Hello, happy Monday. Our warm-up question today is, how many orientations can a p orbital have? Take a minute to answer, revisit your notes from Friday, and pause the video if you need to take some time to write down your answer. Hopefully you were able to say that a p orbital can have 3 orientations. In our second energy level, we can see we have p sub 2px, 2py, and 2pz. Right. Today we're going to be talking about wave-particle duality and how our past understandings of how energy behaves influence how we now think about it. Our learning objectives are, I can compare the ways in which light behaves like a wave and the ways in which light behaves like a particle, and I can calculate the energy of an atom when it emits or absorbs a quantum amount of energy. So we know that energy behaves like a wave in some ways. And one of the principal ways that we talk about that is by talking about the speed of light. So C equals nu lambda, where C, of course, is the speed of light, 2.997925 times 10 to the 8th, or 3.0 times 10 to the 8th, depending on how many significant figures we're looking for, meters per second, and that is electromagnetic radiation in a vacuum, that speed. We have nu, which is the frequency or number of cycles per second. And we have frequency is measured in hertz. Then we have lambda, which represents the wavelength, which is the distance traveled in one cycle, which is when we look at measuring lambda, we measure from point to point. So that would be from crest to crest or from trough to trough. Lambda, or wavelength, is measured in nanometers, picometers, or angstroms, and that would be 10 to the 9th meters, 10 to the negative 12th meters, or 10 to the negative 10th meters, respectively. Should be noted that angstroms are not an SI unit, but they are oftentimes convenient when we're talking about wavelengths, specifically electromagnetic radiation wavelengths, because of the scale. When we talk about frequency and wavelength, another important factor often to consider is the amplitude of a wave, which would be the height from the top of the crest to the depth of the trough. And amplitude is expressed in, if we're thinking about light energy, the apparent brightness. So something that is brighter has a greater amplitude than something that is dimmer. A light that is dimmer has a smaller amplitude. And here is a nice little depiction of several different waves. If we compare the green with the blue wave, this is a great example of the inverse relationship between frequency and wavelength. The green wave, we can see, has a much higher frequency, but its wavelength, so if we look from this point to this point, is much smaller than that of the blue wave. The blue wave has a much lower frequency, fewer cycles per second, but the wavelength, so from there all the way to there, is much greater. As frequency increases, wavelength decreases. And because we know that energy behaves like a wave in many instances, it's sometimes good to refresh our memory on some of the other ways in which we describe energy behaving versus the way matter behaves. And 2 examples that we're going to look at are refraction and diffraction. So if we have a pond, we're looking at a pond, we've got one medium above the pond and a different medium in the water. We've got air and then we've got water. If we throw a pebble into that pond, some matter, it is going to change its speed and it's going to change its trajectory. So that pebble is going to slow down when it hits the water, and it's going to go from moving in a straight line to somewhat of an arc. However, if we talk about energy moving from one medium to another medium, say for example, that same air to water instance, the energy is going to refract. It's not going to change its speed or trajectory. It's simply going to change its angle. And it could disperse depending on what type of medium we're going through. So if we're talking about like shining light through a prism, it's going to disperse into its separate different colors. Another example of how energy and matter behave differently, and another classic kind of defining behavioral difference, is diffraction. So if I am standing in a room that has a doorway into another room, and I throw a bunch of sand towards that doorway, the sand is going to continue in a straight path unless something blocks it. The sand that hits the wall right next to the doorway is going to stop. The sand that does not, the sand that goes through the doorway is going to continue in a straight path. It's not going to change trajectory or speed. It will simply continue until it stops because of friction and other forces and things like that. So the matter is going to keep moving in a straight path. If I have energy, so for example, in this case, we'll use sound. If I'm standing in one room playing music, which is a form of energy, and I'm looking ahead to the next room, I can hear the music no matter where I am in that second room, even if they're totally soundproof, because of that open door. The energy is going to bend and move outward in a semicircular path from the doorway and continue to propagate into that second room rather than continuing in a straight path. Ooh, pardon me. So that energy is going to bend. And if I have, for example, two doorways, that music that is playing will continue to move through both of those openings, both of those doorways, but the waves will eventually interfere with one another. I'll get some constructive interference where two wave crests meet, and then some destructive interference where a crest meets a trough and they cancel one another out. A very classic example of this, if you would like a depiction, is the two-wave slit or two-slit experiment, where we've got energy that's being propagated from here, passing through two slits. We'll see some constructive interference here and some destructive interference in the black zone. And it will produce a pattern so this would be not sound energy, but rather light energy. You can find some good YouTube videos of like 1 and 2 slit experiments using lasers that will produce a pattern that looks something like this: constructive and destructive interference. So we know and we have seen that energy behaves like a wave. However, there were 3 big phenomena that were not explained by this current understanding of energy. And the big ones are black body radiation, the photoelectric effect, and atomic spectra. So we're going to talk a little bit about each of those and how they produced new understandings, with the exception of atomic spectra, which we'll go into more detail tomorrow. So the first issue, the black body radiation issue, is basically this. When materials are heated to a high enough temperature, they will start to emit radiation as light. So they'll start to emit electromagnetic radiation. As that material is heated to higher and higher temperatures, the wavelength of that electromagnetic radiation changes as well. And basically, there was just no explanation for why this was happening. You heated something up and it would emit radiation, and then you heat it up more and it would emit radiation at a different frequency. And so Max Planck proposed this idea of quantization of energy. So that basically materials can only emit or absorb certain quantities of energy, certain like packets of energy. And he explained it with this formula: E equals NH nu, where E is the energy of the radiation absorbed or emitted, N is a quantum number or a positive integer, nu, of course, is the frequency, and H is a new constant that we're introducing. H is Planck's constant. It is 6.626 times 10 to the negative 31st joules times seconds. And so this is the important idea of quantum amounts, or of quanta, quantum singular, quanta plural. This is a packet of energy, a fixed amount of energy not slightly less or slightly more, but exactly a certain amount of energy. Again, my apologies. And so if we're talking about atoms in this instance, the energy change between energy levels is always going to be n equals 1. So we're talking about one packet of energy to move up or down a level, so to absorb or emit a fixed amount. So when we're talking about the energy change to change energy levels in an atom, delta E, our energy change, is equal to Planck's constant times nu, or frequency. All right, the second complication in explaining energy as a wave was this photoelectric effect. There are kind of two components to the photoelectric effect conundrum. Basically, the photoelectric effect is if you shine a wave, or shine a light of a high enough frequency at a metal plate, you will observe a current. And there are two issues with this that were not well explained. The first being that there appeared to be a minimum frequency, a frequency threshold, where if the light didn't have a high enough frequency, no current would be observed. The second issue was that there was never a time lag. So as soon as you shone the light, there either was a current or there was not. There was never any sort of charging up time. And this led to the explanation of energy as a photon. So this is where Einstein comes in. And he takes Planck's idea of these packets of energy and says, well, if energy is a fixed amount, what if it also is like a particulate? It behaves like a particle, which he called a photon. So a photon represents a fixed amount of energy, a quantum of energy, if you will, and explains away the two inconsistencies with the photoelectric effect. So the energy of a photon is equal to that energy change from one energy level to the next in an atom. So that means the energy of a photon is Planck's constant times nu, and that means that energy is frequency dependent. So that explains why the light has to have a minimum frequency in order for there to be a current observed. Additionally, if we're understanding energy as a photon, there will never be a charging effect because atoms have to absorb a photon of a high enough energy in order to release that electron in order to induce the current. So a dim light of the correct frequency will have fewer photons of high enough energy, but there will still be enough photons of high enough energy to induce a current. There will still be enough high energy photons to cause those electrons to pop off and induce a current. If the light doesn't have the appropriate frequency, however, there won't be enough photons absorbed of high enough energy to release electrons, so there won't be a current. So basically, explaining energy as a photon, as a particulate, allowed us to better understand or better hypothesize why the photoelectric effect was such a confusing point. The atomic spectra is the third point of contention with the wave-like model. Basically, if you vaporize and then excite an element, it then emits electromagnetic radiation. You shine that through a slit and then through a prism, and what people believed you would see would be a continuous spectrum. However, what was actually observed was what was called a line spectrum. So you had discrete lines at different wavelengths. And this was very contrary to what was what people believed would happen, because it was understood that if an electron is moving around the positively charged nucleus, eventually it's going to spiral towards that nucleus, and as it does so, it will be continuously emitting radiation. So it should be a continuous spectrum. However, we end up with this discrete guy, and it's confusing because it doesn't make any sense. Scientists are able to use data to come up with this equation, to explain and to predict where those wavelengths will be. So 1 over lambda, or 1 over the wavelength, is equal to r times 1 over n sub 1 squared minus 1 over n sub 2 squared, where n sub 1 is always going to be less than n sub 2, and n sub 1, if we're looking for the visible light, because you can use these spectra to produce, you can use this technique to produce spectra for the IR and the UV ranges as well. But if you're looking for the visible range, n sub 1 is always going to be 2, so n sub 2 is going to be 3, 4, 5, et cetera, et cetera. And r is our Rydberg constant, so 1.096776 times 10 to the 7th meters to the negative first. But like I said, this was an equation that was derived from data. There was not an explanation for it yet. We'll talk more about why that explanation, or what the explanation ends up being, tomorrow. However, all three of these issues, of these phenomena that contradicted the wave theory, produce what we now call the wave-particle duality. In order for us to move forward and continue to study and understand, especially electrons as energy, we have to accept that it behaves both as a wave and as a particle. So keep working on your practice problems for the week. I'll see you tomorrow.